I'm a consultant. I'm doing some work for Retevia, is a company founded last year in the US by Lee Howard, and it specializes on IPv4 as a service. So the idea behind this is networks, IPv4 is expensive, IPv4 is scarce, and running a dual stack network means you have double the work. You have to configure v4 and v6, you have to manage v4 and v6, monitor v4 and v6, secure v4 and v6. So the whole idea behind this is just get rid of v4 in your core network and deliver it over the top, translations, tunnels. For example, in data centers, this is what Facebook does. They have their data centers IPv6 only on the inside. There are many big ISPs in Europe and the US that do this on their home connections, and it saves a lot of effort and money. Your core network is much simpler, your addressing plan is much better, and your customers can still use IPv4, but it's less of a burden on your network. Now the problem is there are many technologies to do this with. So I'm going to discuss several of those technologies and compare them and see which ones are better for which customer groups, for which purpose. The most well-known one is NAT64. So how NAT64 works is the client is IPv6 only. It works together with DNS. So the client says, I want to connect to www. Some IPv4 only website. Now the client has only IPv6, the server has only IPv4. What the DNS does is it gives an IPv6 answer where the IPv4 address is part of the IPv6 address. So the client thinks, oh, this server has IPv6, it makes a connection to this IPv6 address, and then the NAT box sees, oh, they're connecting to this v6 address, so what they mean is they want to connect to this v4 address. And then the NAT box translates it to v4, but for the client, it just looks like the whole world is already IPv6. This technology is used a lot in guest Wi-Fis, it's used in mobile networks a lot. Some of the biggest mobile carriers in the US run this technology. And it's so popular because the mobile operating systems work with it. Apple has said for their App Store guidelines, if you do not support networks like this, you cannot upload your app to the App Store. So Apple just refuses any app that is not compatible with this technology. Android has done it a little different. They use 464XLAT. And 464XLAT is basically an IPv4 simulation. On the device, it looks like there's IPv4, but then the device converts it to IPv6, knowing that the NAT64 gateway will convert it back to IPv4. So this way, the application developer doesn't need to do anything. It just looks like everything is dual stack. So this is a very common technology and used very much. Now it also has a couple of downsides. Like every NAT technology, it is stateful, which means that the translation device has to remember each and every connection. Because it's natting, it has to remember which address is natted to which address. So this makes it really difficult to scale. There is, if you go up to like 8 gigabits of traffic, actually there's an open source solution called Jool, J-O-O-L, and that one can actually work in a cluster. So you can have multiple NAT boxes who synchronize amongst each other, and if one of them fails, the other ones just pick up where it left off. So, but if you don't have this, or if you need bigger bandwidth, then it quickly becomes a single point of failure. If your NAT box reboots or has a problem, then those customers go offline for a bit. It's also less traceable. If you, for example, the government says we have to monitor this user, then as an ISP, it's much harder to do that if you run a NAT service. And if you want to keep track of what everybody's doing, so if somebody sends in a complaint afterwards and you want to trace back where it came from, it requires a lot of logging. And the last time I talked to somebody, they were measuring it in gigabytes of data per user per day. So this is quite a lot of storage you need for this. But like I said, depends on your needs. For example, mobile networks, this is the most used technology. Then another one that's already fairly common, especially in Europe, where I come from, is DS Lite. DS Lite works together with the CPE, with the little router at the user's home, if you have a cable or fiber or DSL. It's also a well-known technology, and what DS Lite does is it builds a tunnel. So the backbone is IPv6 only. The user's home network has IPv4, and whenever the user does something, it's sent over a tunnel to a central box at the ISP, and there the ISP will NAT it. So the problems it has are basically the same as NAT6.4, because the ISP needs to build a central huge NAT box. But it's also for the home user very easy, because as far as the home user can see, they have dual stack. They have both IPv4 and IPv6. So for the home user, nothing much changes. Most things just work. The ISP's core network is only IPv6, so it's easier to maintain, but you need this very big NAT box that's a single point of failure. So different use case, also a solution, but there are better ones. The next one I'm going to talk about is called MAP-E. And we actually have one of the authors of the RFC that's the basis for this here in the room, Jan Zorc from Slovenia. This is actually a very interesting technology, because what this does is it also builds a tunnel between the home router and a central router at the ISP, except it's stateless. Instead of doing the NAT at the ISP, it lets the user do its own NAT, just like we had with IPv4. So this is more like a model that we are used to in terms of capacity and performance. It does this by splitting up IPv4 addresses. With normal IPv4, it worked like, okay, one customer gets one IP address, then another customer gets another IP address, and each customer gets a whole IPv4 address. With MAP, which stands for mapping of address and port, it's split up. For example, the first customer gets IP address 1, ports 1000 to 2000. The next customer gets the same IP address, but ports 2000 to 3000, etc. So in this way, you can actually use a single IP address for multiple users, which makes it much more efficient. You don't have to buy as many IP addresses. The core of the network is still v6 only, because these are IPv4 over IPv6 tunnels. And because it's stateless, you don't need one translator. You can have multiple around your network. And it doesn't matter where the traffic ends up, because it's a fixed algorithm. It looks at the v4 address, it looks at the port numbers, and it just knows where to send the traffic. So if one packet goes through one translator, the other packet goes through another translator, it just works. And this makes it a big advantage, because now, if you don't have enough capacity, just add another box. You want more capacity, add another box. Want some redundancy, or you want to do translation in a different part of your network, add another box. You can just keep expanding without any scalability issues. And because this is a fixed algorithm, if somebody has a complaint, he says, oh, I got an attack from this IP address, this port number, you can just look at the algorithm and say, oh, that port number belonged to this customer. You don't have to log anything, you just can calculate where it came from. And there are tools on the internet that can help you do this. Cisco has a very good map tool where you can do calculations of which IP address and which port number belong to which customer. So I like MAP-E also because it's a clean solution. You have an IPv4 packet and you just put it in a tunnel. You put it inside a v6 packet, you send it to the translation router, and the translation router just takes the v4 packet out and sends it on. So it's normal IPv4. It's just that the translation router determines, according to the port number, to which customer to send it. But the protocol itself is just v4 and v6. Now the next one is MAP-T. And this is actually a funny one, because there are two versions of MAP. And some people were in favor of one of them, some people were in favor of the other of them. So in the beginning, they just flipped a coin to decide which one would be the standard. By now, both of them have been standardized, so it's no longer a point, but it's just to make to show you that between MAP-E and MAP-T, there is no one that's absolutely better. Some people prefer one, some people prefer the other. Now, what MAP-T does is translation. So MAP-T actually doesn't put the IPv4 packet in an IPv6 packet. It actually translates the v4 packet into a v6 packet. then sends it across the network, and the translator reverses the translation and turns it back into a v4 packet. So I don't like this because it messes with the packets. It doesn't send them on cleanly. It translates them and then translates them again. But it has some good advantages as well. Because the packet is translated, you can see from the IPv6 destination what the intended IPv4 destination is. Which means in your routing table, you can actually make more specific routes that say, oh, if it goes to this data center, send it to that translator. If it goes to this customer, send it to that translator. So you can do more specific routing and direct the traffic better in your network. With MapE, they just send it to one gateway address, then one of your gateways picks it up, and then it's IPv4, and then the v4 routing applies. With MapT, you can actually apply IPv6 routing to steer the traffic towards the right translator. So even though it's messing with your packets a bit, it does offer some extra features. And for example, blocking. If you want to block a certain v4 address, you can already just block it for a certain v6 address because there's a mapping between them. So you can drop traffic earlier in your network. If you want to blacklist a certain IP address, you can do it closer to the sender, so you don't have to carry it throughout your network. So there are advantages. Then the next one is lightweight 4/6. And this one is actually funny because the RFC is written in the style of DS Lite. This is basically a protocol that is written in the way that for people who know DS Lite, it's easy for them to understand this. If you look at the used technology, it uses the technology of MapE. So this protocol is like halfway between DS Lite and MAP. What this does is, it doesn't use an algorithm, but everything else is the same as MapE. So instead of calculating the port number and the IP address, this one you actually provision each user individually. You say this user gets this IP address and these ports. This user gets this address and these ports. So you have more control exactly over who uses which addresses. This also means that the configuration is much harder, because every time you add a customer, every time you change a customer, you have to update all your translators so they learn what the configuration for this specific customer is. And in Germany, a big ISP actually had a rule list of 2 million lightweight 4/6 rules because they had 2 million customers. So the scalability of this is much harder, but it gives you extra control. So it's a different version. It offers benefits, but it also has its downsides. So these are basically the protocols that you can use to provide IPv6 to IPv4 to a user that's on an IPv6 only connection. All of these technologies are good for providing IPv4 without having your whole backbone to support IPv4. You can upgrade your backbone, just get rid of v4 and have a very clean, simple to maintain v6 backbone, and then just do IPv4 in tunnels or translation. So how do you choose? How do you choose which technology to use? Well, if you're talking about mobile networks or guest Wi-Fi networks, I would go with NAT64. Because this is the proven technology for these types of networks. It's used by very large ISPs. I know that Microsoft was actually looking at this. They had some problems with VPN software, but it is the preferred solution for this type of network. Then I would say, okay, do I really need to have per user configuration? Does every user need a specific configuration, or can I just have one general algorithm that does it? If you really want different configuration for each user, you need lightweight 4/6. That's the only technology that provides this. But if you don't need that, you can go for the easier solutions. And then you can look at like, okay, do I need to do filtering inside my network? Do I need to have different gateways for different exit points in my network? If you need that, then MapT is the solution, because MapT offers these features. If you don't need that, then MapE and MapT are basically equal. So I personally would prefer MapE because the implementation is cleaner, but at that point it doesn't matter that much anymore. Both of them are valid solutions. As you can see in this diagram, there is no DS Lite. I decided to leave it out because DS Lite was very popular in the beginning of this technology. It was the first protocol that could do this. By now, I think MAP and Lite 4/6 provide much better solutions for the same problem. So if you would start today, I would not do DS Lite anymore. The only advantage that DS Lite still has is that it's supported in more home routers. The support is a bit better. But I've run all of these technologies on, for example, OpenWRT, and they all just work fine. So with that kind of technology, you can use any of them. So I would recommend MapE or MapT for new deployment. Per user provisioning, okay, you need Lite 4/6. If you have a mobile network, go for NAT64 because that is the solution that Android and Apple fully support. Now there's another one, and this one has a completely different use case. This is for data centers. So if you have a data center, again, managing both IPv4 and IPv6 can be a great burden. All your firewalls, you need to think about both protocols. Your addressing plan, you always have to think about IPv4 as well. You can't just have a clean IPv6 addressing plan. So for data centers, I recommend a standard called Siit DC. And this stands for Stateless IP and ICMP Translation for Data Centers. Your whole data center can just be IPv6. But of course, you still have customers that don't have IPv6, that only have IPv4. So what this does is, it basically is the opposite of MAP, the opposite of MapT. So instead, you run your whole data center on IPv6, and you put a translator at the edge of your network that says, okay, if somebody tries to connect over IPv4, we translate it to IPv6 for them, and then we can process it in the data center. And the answers that go out get translated back to IPv4. So this is again, a stateless solution. So if you need more capacity, just add more translators. If you need more redundancy, add more translators. This is a very nice technology, and this is basically what Facebook uses to run dozens of data centers around the world. This is good technology. And again, for this, you also have open source software. The same Joule that I said, the open source NAT64 software, also supports this technology. So you can just have a Raspberry Pi that performs this function for you if you want to. A very small server, all of them would work just fine for this. So it provides a lot of benefit, IPv6 only data center, easier management, less maintenance, and great capacity and scalability. So this is a very good technology as well in my eyes. Now, scalability. How far does this scale? Because people are worried like, oh, I need extra translators. How much performance will I lose with this? So we did some testing, and with NAT64 and DS Lite, it's hard to scale. I manage with redundancy up to about 8 gigabits of traffic. So based on open source software, so cheap to run, there are definitely Cisco boxes that can do much higher bandwidth, but you will pay a lot of money for those. Now this one is much more interesting because we've tested this using open source software that comes from Cisco, and it's called VPP, Vector Packet Processing. And it's a very efficient algorithm to process packets on an Intel server. So we had a dual socket Intel Xeon server, and we managed to get up to 185 gigabits of traffic at about 83 million packets per second on a standard Intel server. So, of course, we needed good network cards, so we used Mellanox 100 gigabit network cards. And we expect the next generation of hardware, which has better PCI buses, to easily scale up to 400 gigabits per second. It's actually the problem of the PCI buses. The processor is fast enough, it's just the backbone inside the server that is the bottleneck. Next year we will get PCI Express 4.0, which will have double the performance that we have now. Plus we're getting new AMD processors, which have lots of PCI Express buses. So with more buses and higher speeds on each and every lane, we can achieve much higher bandwidth. I wouldn't be surprised if this goes up to 600 or 800 gigabits with enough CPUs. So this is based on open source software. This one is a bit more difficult to manage because it's really a rough component, but it can scale really well. It's redundant, all of them are stateless, so if one box isn't enough, add another box. And then there's also some legal implications, because if you're doing all this translating, usually governments aren't too happy with it, because all this translating adds complexity. So governments usually want to be able to trace back. If they see somebody attacked something on the internet, they want to go back and see who it was. So adding this extra layer of translation or tunneling, you have to have good logging and good facilities to support this. Now, how you do this depends on the type of NAT you do. A TCP session is a 5-tuple. It has the TCP, it has the source IP address, it has the source port number, it has the destination IP address, and it has the destination port number. So those 5 elements together define a session between a client and a server. Now, if you do NAT and you just do random assignment of addresses and ports, you have to track each and every one of those combinations. So like I said, this can be gigabytes per day if you need to store all this. But you can also do a different trick. You can also say, okay, I'm not just randomly assigning, I'm actually saying these port numbers are reserved for this customer. And every session the user starts is done from that set of port numbers. And suddenly you don't have to track everything anymore, because if somebody says, who was this user? You just know that those ports belong to that customer. So depending on the NAT algorithm, you need more or less logging. So what are the advantages? Well, if you do the 5-tuple based version, you can do more efficient use of your port numbers, because everybody can use any port number and you can mix all the things. But it's more complex. Again, if you use this, then protocols like stun might have some problems as well. If you do it based on the 3-tuple, you have to reserve port numbers for a user. So maybe your usage is a bit less efficient, but it's more effective. Now, if you look at the A+P based protocols, they're already built around the 3-tuple concept. They're already built around giving certain ports to a certain user. So with this one, you don't even need to log anything, because the whole concept of who has which port number is built into the protocol. So so MapE, MapT, Lite 4/6, they require almost no logging at all. So if you look at it, like I said, you have the protocol, TCP, client address and port number, public address and port number, and destination address and port number. And I exaggerated a bit in this example, because you can see that the public address and port number is the same for everybody. But because the destination is different, each of these lines is still a separate session. This would be the most efficient way to use your IPv4 addresses, but the most expensive to log. If you do it the other way, the way A+P does it, or if you use a NAT that does 3-tuple assignments, then you don't have to care about the destination. This is also good for the privacy of the user, because if you actually have to log every single session, you have a log file that says exactly which user accessed which Facebook page at which time. You get very, not the page, but the service. You get very detailed logging. It's a lot of data, and for privacy of the user, this might not be what you want. So if you do it on the 3-tuple based algorithm, you don't need to log that much. It's cheaper for you to log, it's better for the privacy of the user, and of course if the government wants to say, oh, I still want to know what this user is doing, you still know which port numbers they have, so you can check it anyway. But you don't have to log it for everybody. So yeah, this basically repeats what I just said. 5-tuple logging reveals exactly who communicated, and it's a massive amount. 5-tuple logging has a low or no need for logging, but usually still provides enough information that the government is happy with it. And that's a repeat again. And with that, I'm done with my presentation, and I would like to take some questions. Anybody wants to know something? Is everybody awake? Ah, Jan and Ishal. Yes.
Sander, thank you for this presentation. Yanni here, the original author of that thing there, A plus B called. I would just like to add, when we discuss a lightweight 4/6, one of additional features that people liked a lot when we wrote the signaling was that you can actually dynamically allocate additional ports if a user runs out of the ports, because with MAP-E and MAP-T and any stateless A plus B mechanism, you have fixed set of ports. If you run out of ports, you're done. With lightweight 4/6, I don't like it very much because it's stateful with as much statelessness as possible. But yeah, you can allocate additional set of ports, and that's the reason why people also like it.
Thank you. I'll add that to my next version of these slides.
Thanks for that presentation, Sander. This is Kevin. So I have two questions. My first one is from the point of view of a service provider. Let's say you're an ISP providing service and you want to do this. What sort of what hardware do you need on the box to do the, for example, the NAT64? How much hardware do you need to do that? Let's say an ISP with 200 Mbps to sell. What type of bandwidth or what type of hardware do they need for this? That's my first one. Second question is, where does the translator box sit? Where does the translation box sit in your network? Is it between your edge and your customer? Where exactly does the box sit? And how many of these boxes should you provision to avoid incident? To have some sort of failover? Can you have them talk to each other and have some sort of redundancy?
So yeah, so for the net performance, like I said, up to 8 gigabits, you can easily do it with open source software. If you're talking higher speeds, I know, for example, ISPs that use A10 hardware that does this. And last I saw, they charge for a big box that can handle like, I think, 40 gigabits of capacity. You're paying about $50,000. So that's the prices I've seen. I've also seen that Cisco can do it if you have the ASR 9000 range. But the complaint was that the prices were about 20 times as high as A10. So that Cisco really prices itself out of the market with this. So yeah, I would go for 50,000 for a box that can do 40 gigabits or 80 gigabits of speed. In terms of where you place it, I don't know. I know that Deutsche Telekom is looking at lightweight 4/6. I don't know where they place the boxes. The US customer that we are dealing with is one of the larger ISPs, and they have 16 regions in the US where they provide service. And I can't name their name, NDA, but the idea is they have 16 regions, and each region has, close to the edge, 2 translators for redundancy. So usually you want it as close to the edge as possible, because between the translator and your edge, you need v4 again. So the closer to the edge you place your translator, the less IPv4 maintenance you need to do in your core.
My question, what is the differentiate between NAT and port address translation, and when we are using port translation?
So NAT is the technology where you translate in a device, and you have to remember each and every session. So this is used by DS Lite and by NAT64. There you need, as an ISP, you need a translator box that translates every session individually. MAP-E, MAP-T, and lightweight 4/6, the ISP doesn't do any NAT. It only forwards the IPv4 packets to the user, and then the user can do their own NAT, just like they did in the normal IPv4 world. So the main difference is where you put the NAT. If you put it at the ISP, you need a huge big box, because that single NAT box needs to translate for all the users. If you use the A+P protocols, MAP-E, MAP-T, lightweight 4/6, then you move the NAT back to the customer, and each customer has their own little NAT router, which obviously scales much better because you distribute the work over all your customers. So that is the main difference. Did that answer your question?
How is the NAT is it on the ISP side or how?
So, like I said, the NAT 6.4 and DS Lite are on the ISP side. So they usually require quite a big investment on the ISP. MAP-E, MAP-T, and lightweight 4/6, the map is on the client side. It also, by the way, because it's on the client side, the client can do things like port forwarding for themselves. If you have a central NAT, like NAT 6.4 or DS Lite, the client cannot do a port forwarding. So this is actually something that I didn't mention, but this is for the user's perspective, this is an important difference. And where you do it in the ISP network, I've seen offices where they do NAT 6.4 just for the public Wi-Fi. So there, the NAT 6.4 box is in the office building. If you have a mobile carrier, the NAT 6.4 box is in the ISP network. So it depends a bit on what the scenario is, but all of those are possible. With MAP-E, MAP-T, DS Lite, MAP-E, MAP-T, lightweight 4/6, it's always the ISP who does it, and the box is as close to the edge as possible usually.
Hi, I have something I don't get it in there. When we use MAP-E and assign a specific port for client, we know every service have it use a special port. What's the logic of the port that I assign to the user with MAP-E and the port that use with the services? How can I differentiate them?
So what MAP-E and MAP-T do, I haven't shown the slide here. What they do is they look at the IPv6 address, and as an ISP you say, okay, you know, my customers are in this prefix. Then the next few bits in the address are the customer number. And then after that is the subnet within the customer's network. So you define this in your addressing plan, in the translator, and you say these bits in the v6 address are the customer number. And then what MAP-E and MAP-T do is they take the customer number, they use the first set of bits from the customer number to build the IPv4 address. So you say, okay, I have this pool of IPv4 addresses. So the first bits are used to determine what the IP address is, and the last bit of the customer number determines which ports the customer gets. So all the addresses and ports are calculated from the IPv6 prefix. So this is the algorithm, and this is the most complicated part about MAP-E and MAP-T, because there's this take some bits from one address and use them to construct another address. That confuses people. But once you get used to that, it's actually not that hard. There's a good I forgot the name. Is it the map tool from Cisco? Yeah. Can I steal a browser on this?
We don't have much of time.
Oh, okay. In that case, I'll quickly show it. Cisco map tool. The map simulation tool, that's the name. And here in pretty colors it shows this is the v6 prefix, the green bits are the customer number, and then part of the green bits end up in the v4 address, and parts of the green bit end up in the port number. And this is how the port number and address are constructed. So if you want to play with this, I can recommend the map simulation tool from Cisco. It helps understand the algorithm.